Hi everyone, so in this video we are going to take a look at linear differential equations. So in class we're going to talk about methods for how we can find solutions to first order linear differential equations. So in this video I want to just focus on being sure we're able to identify what a linear differential equation is. So we've seen this terminology before. A linear differential equation is a differential equation which can be written in this form. Okay, so this here is an nth order differential equation. So we could have linear differential equations of any order. But what's important when we're trying to identify this is, first of all, you'd want to identify what are the dependent and independent variables based on the context of the equation. So in this case, we have an independent variable, which is x, and we have a dependent variable, which is y. And so we kind of organize each of our terms that have a y in them like so. So this would be like the nth derivative of y, the n minus 1 derivative, the first derivative, and all the way down to the 0th derivative. And as long as each of the derivatives themselves only occur at most to the first power, and the expression that comes in front of each of those derivatives, as long as that only depends on the independent variable x, then you've got a linear differential equation. So there's a lot of moving parts here. So let's just review this idea for a couple of examples. And then we're going to be looking at much simpler cases for just first order differential equations. So let's consider this example. 3e to the t, fourth derivative of z minus 2t squared times the derivative of z plus 3z natural log of t minus cosine 4t plus 7, all is equal to 0. That's a really bad looking differential equation, but it happens to be linear. And I can recognize this because here are each of the places where a z occurs. And each time a z occurs, it only occurs at most to the first power. So that one is indeed linear. If we move down to the next one, for this one, let's say we want to look at the derivative of y to the third power is equal to 6x minus y. And this one is non-linear because of this power over here. So having a third derivative is not a problem, but taking the first derivative and raising it to the third power, that would make it non-linear. And one more example, if we had the third derivative of y minus 2y times y double prime plus 2xy is equal to 4 cosine x. This one is non-linear, and notice our third derivative is to the first power. We have a y here to the first power, a derivative, second derivative, and y. But what the problem is, it's right here with this term over here. So we have a second derivative of y, but the expression in front of it depends on y. And for a differential equation to be linear is the only thing that can be multiplying a derivative of y should be some expression that doesn't have y's in it. So this one would violate that. So here's some examples of linear and nonlinear higher order differential equations. On the next slide, I want to just focus on first order differential equations. And so the situation that we'll be thinking about initially is going to be much easier. So when we have a first order differential equation, we're not going to have any derivatives with an order bigger than 1. So that definition that we had on the previous slide gets truncated quite a bit to we have a first derivative. Multiplying the first derivative can't be any y's. It can be only something that has x's in it. Then we have a 0th derivative, and what's multiplying that shouldn't depend on y. And then we can have some other expression that should only depend on x. So it really matters identifying which variable is independent and which is dependent. And just to review, what we talked about in last class was how we can identify whether differential equations are separable. So down below, we've got 4 different differential equations, and I'd like to just practice identifying whether each of these is linear And while we're thinking about it, we might as well consider whether they would be separable as well. And I think a good first step in this process is identifying what are the independent and dependent variables in the differential equation. So in differential equation 1, we have t times x prime plus 3x is cosine of t. So our independent variable is t, our dependent variable is x. And so I can see that this differential equation is exactly of this form. I have a derivative, first derivative of x. It's being multiplied by something that doesn't depend on x. I have a zero derivative of x. I have x over here. It is linear. It's being multiplied by something that doesn't depend on x. And over here, we have some expression. It doesn't need to be linear of our other variable t. So this one over here is indeed linear. And is this one separable? Well, let's see. To determine whether or not this is separable, it's useful to put it into this form. So in 1, we could bring the 3x to the other side by subtracting it. And then we could divide everything by t. Okay, but the problem is the right side can't be written as something that only depends on t's and something that only depends on x's. I've got this difference in the top, so I can't write this as a product of two expressions. One only depends on x and one only depends on t. So this is linear, but it is not separable. If we were to take a look at 2, now we're looking at x times the derivative of y with respect to x plus 3y squared is equal to 0. So now our independent variable is x. That's our input, and the output is y. So I want to see, is this linear in y? This term is fine. This term is not, right? I have y to the second power. So this is definitely not linear. But it might be separable. So in order to see whether it's separable, we can subtract 3y squared from both sides. And then we can see, yeah, actually this I could separate because the other side of the equation can be written as minus 3y squared times 1 over x, if I divided both sides by x. So this one is separable. So the first one was linear but not separable. This one is not linear, but it is separable. And identifying the type of differential equation that you have, again, this is going to be really useful because it will help us identify what sorts of methods can we use to solve the differential equation. Okay. Differential equation 3, we've got p times dp dt equals natural log of t. This one is not linear because we have a dp dt being multiplied by a p. So the stuff that's being multiplied by the derivatives shouldn't depend on the dependent variable, and this one does. So this one is not linear. But you could really quickly check that that one we could separate as well. So this one is separable. And then lastly, looking at 4, this one is linear because I can take this equation e to the t times y prime is equal to 3t cubed y. And this is equivalent to saying e to the t times y prime minus 3t cubed times y is equal to 0. So that is linear. Our independent variable is t and the dependent variable is y. So each of the expressions of y and y prime, they're being multiplied by things that only depend on t. So this one is linear. And as well for this one, you could check that this one is also separable. So there's really no connection between if something is linear, can it be separable or not. So it's possible that a differential equation is linear and separable. It's possible that it's neither linear nor separable or any other combination. So take a look at the reading quiz and practice similar examples as this. And then in class, we'll talk about how we can come up with a good method for solving first order linear differential equations. Thanks.